There we go. Okay, so I'd like to do that last problem that you have. If somebody would read it for us, please. Should start with what is the magnitude of the centripetal. Lauren, thank you.
What is the magnitude of the centripetal acceleration?
Okay, so let's just start with that. So we want to find the centripetal acceleration, or the magnitude of it. And what is our formula for centripetal acceleration? V squared over r. Doesn't really matter if you use a capital R or a lowercase r, so let's not get too crazy about that. Okay, it's the one place where I actually don't care. Big T and little t are different things, as we'll find, but r's don't really matter much. Okay. So what do I need to be able to answer that question? I need V squared and R. So how about R? What is R? The what? Radius of the Earth. Can you find the radius of the Earth? You can probably look it up. So what's the radius of the Earth? Okay, so 6,370 kilometers, which I'm just going to convert to 6.37 times 10 to the 6th meters. And then I need V. How am I going to find V? Okay, how is finding the period going to help me, Annabelle? Okay, so the period is how long it takes me to do one rotation of the Earth. And how does that help me? Anybody? Sophie. I don't want to do that yet, because that's going to be a lot of work. I want to know that doing that is going to help me somehow. I don't want to do the busy work of finding the period in seconds if it's not going to be useful. So how am I going to use that, Dagny? Okay, or at least on the equator. Let's.
Then you can take the time or the period and use that as your time and your distance.
And what's my distance? Okay, so it's going to be the circumference, which is 2 pi r. Okay. So yeah, finding the period now and converting it to seconds is going to make sense, but I didn't want to go through all of that if I didn't know it was going to help me. Okay, so then what is the period of the Earth's motion? I don't need it in seconds. What is it? 24 hours. And then I'm going to convert that 24 hours into seconds. And what do I get for my period? Yes. Okay. Sig figs are a little iffy here. A day isn't really 24 hours anyway, so we'll just kind of keep what we have for right now. Okay. And probably use this as our sig fig limiter, okay, because that's a number that was measured. Okay, so I know that AC is V squared over R. So that's going to give me 2 pi R over T squared divided by R, right? If I just substitute in. I realized there was a bunch of stuff. Okay, and so this is going to give me, should be 4 pi squared R over T squared. And before you ask me why the R isn't squared, think about it yourself. And then we can substitute everything in. And let's say we have 3 sig figs. We'll take the number from the radius of the Earth and we'll limit it that way. What do you get? What'd you get, Annabelle? Fiona's nodding her head. So what other people got? Okay. All right, so how about part B? What does part B ask us to do? This was A. Somebody read us part B. Somebody other than Lauren. Dagny, thank you.
What was the period of rotation of the first path to be for object in the theater on its phase turn to have a centrifugal acceleration with a magnitude of 9.8 meters?
Okay. So now we want AC to be 9.8 meters per second squared. And we want to know what the period is going to be. Okay. So because of the way I solved part A, I already have an equation that has AC and T in it, right? I go back a slide, I have this equation right here. Actually, that whole equation right there. Okay, so I know that AC is going to be 4 pi squared R over T squared. And then what do I need to do? Solve for T. So because we're dealing with time, we are going to automatically take the positive root, okay? Because we're looking for the amount of time. And sometimes, as I think we've talked about before, I know I talked with somebody, sometimes negative time has a meaning. and it makes sense if you think about it. But in this case, I just want the number of seconds that it would have to be. So what are we going to get? Okay. Well, let's just leave that there for a moment. Okay, is this what everybody got? Okay. All right. So I don't really have a feel for how long that is. Okay, 5,000 seconds doesn't really mean a lot to me. So why don't we try converting it to minutes and then see if that's something that we can wrap our brains around. So what's this period going to be in minutes? Okay, so let's call it like 84. Okay. So that's about how long? About an hour and a half, okay, give or take. So that would mean that the Earth would make one complete rotation. The sun would rise and set and rise again every 84 minutes or every hour and a half. Which, I mean, no, it doesn't happen. It's just to give you an idea of what would happen if the centripetal acceleration was equal to the acceleration due to gravity. It would be. Our whole world would be extremely different. Sophie. Figure out how far. Sort of. I would actually, it might end up being the same math because actually what you would use are Kepler's laws. And Kepler's law, yeah, it because of the way this problem is set up, yeah, because of the way this problem is set up and the choices that were made, you might be able to figure it out, but it's just kind of like the choices in this problem coincidentally make the symbols the same as they would be in Kepler's laws, which we did in astronomy. So Kepler's laws are really the way you would do it, but you would still need to know the period and the semi-major axis of the orbit. And actually, what the heck was that? You would need to know the mass of the Earth and the radius of the Earth. Well, maybe not the radius of the Earth, but you need to know the mass of the Earth and the universal gravitational constant. But the mass of the Earth, the radius of the Earth, and the universal gravitational constant are all combined into little g. And since you're letting AC be equal to little g, it's just kind of one of those things where it might work, but like the Hubble Space Telescope has a period of about 90 minutes. I don't know exactly what it is, but it's about an hour and a half. So yeah, that's the way to do it. And we'll talk about Kepler's laws in here too. Okay, make sense? You didn't have to understand what Sophie and I were talking about. We'll come back to that and talk about it for real. Okay. All right, so this is the end of uniform circular motion. This is one of those things that we will come back to. We're going to use it in chapters 5 and 6, probably 6, when we talk about friction and rounding a curve. Okay. So the next thing I want to talk about is relative motion. And we'll start by talking about it in one dimension, but you'll see that we'll be able to talk about it in two. And about. They are, it's a little bit of both. If you look, there is like class time relative motion in 1 and 2 dimensions. But but there are not guided notes. I'm probably not going to do that anymore because you should be able to do it. So I just kind of left you a hunk of space that you can extend however much you need to take notes. And then I did type out the problems that we're going to do. Okay. And there was that whole thing that if you come and take the pages, you can keep them being sub pages. So I've kind of stopped distributing them. I can start distributing them again if you want, but. Okay, so everybody grab the notes then, the class time notes, okay? All right, so I like to say that this is one of the 3 hardest things we will do all year. Okay, so if we can work our way through this, then we will be in pretty good shape, and then we'll be ready for angular momentum. And I don't remember what the third thing is. So we'll get to it when we get to it. Okay. So the first thing we have to talk about, and something that you read about, is a reference frame. And your book tends to lean towards giving big philosophical, motivational explanations for what things are. And as far as I'm concerned, your reference frame is the object you attach your coordinate system to. Okay. And it's usually the Earth. Okay. There are situations where it might be something else. Let's say I went on one of those really great big huge cruise ships and I'm going to go jogging every morning and do laps around the deck. Okay. I'm going to say that I jogged, 5K. But as I was jogging that 5K, because that's however many laps it is around the ship, the whole ship was moving. But I don't say that I ran the 5K plus, I don't know, the 30K that the ship moved in the half hour it took me to run my 5K. Okay. Because in that situation, my reference frame, the thing I attach my coordinate system to, is the ship. Okay. Likewise, if you were on an airplane and you got up and walked back to use the restroom and then came back to your seat, if you were going to talk about the distance that you traveled, not the displacement, but the distance, you're going to talk about, the 30 feet that it was to the bathroom and the 30 feet back. You're not going to talk about the fact that in that time the plane traveled 100 miles. Okay. So unless we have one of those wacky situations, we're almost always attaching our reference frame to the Earth. Okay. And what do you know? Go ahead, Lauren. Yep. No. Nope. And that's actually what I was going to say next, is we still know that the Earth is moving around the sun. And in fact, we know that the sun is moving around the center of the galaxy, and that the galaxy is actually moving away from other galaxies. So everything's in motion, but we attach our reference frame to something that's convenient, usually something that's pretty big that you can't tell it's moving. So like if I walk to the end of the room and back, I don't feel that the Earth has moved underneath me. Just like if you can feel the planes moving. But if I walk to the restroom in the plane, if I jogged around the ship, I don't feel like those things are moving with respect to me. It's a little different if I'm walking on one of those people movers in the airport. Okay. And then I can feel that I'm not only walking with respect to this people mover, but by looking around, I can see that the whole people mover is moving with respect to the airport. Okay, so it's a matter of what you can detect, I think, more than anything else. Okay, but basically our reference frame, and often we call it an inertial reference frame, and we'll talk about inertia a little more when we get into the chapter, so sometimes it's inertial. That's usually going to be the Earth, and usually we don't worry about it. And again, for for short distances, I don't have to worry about the fact that the Earth is moving. So when I kick the soccer ball, I'm figuring out, and you do a lot of physics in your head when you play ball sports. You probably don't know it, but you do. When you kick that soccer ball, you pretty much know where it's going to land, even before you learned projectile motion in my class. Okay. You don't have to take into account the fact that the Earth is rotating. However, if I'm going to launch a missile from the United States to Moscow, I have to take that into account because it's going such a long distance. I took that one summer. That was my summer job, was calculating missile trajectories. My friend's dad owned a company and it was a job, so I took it. Looks good on my resume. But then you have to take into account the fact that the Earth is rotating because the object is in the air for so long and the object is moving so fast. So it's still projectile motion, but I have to take into account the rotation of the Earth. It's not a rotational, it's not an inertial reference frame anymore. Yes. Yes, they're not, I don't remember. They are moving fast. I can't remember how fast a missile moves anymore. Probably because it doesn't have to worry about the safety stuff and it's smaller and they're more aerodynamic. But yeah, planes have to worry about that, about how much the Earth has rotated underneath it, which is why your trip from Los Angeles to Buffalo is shorter than your trip from Buffalo to Los Angeles. Because when you fly from Buffalo to Los Angeles is moving away from you, I think. And when you fly from Los Angeles to Buffalo, Buffalo's moving towards you. It's not by a lot. It's not like, it doesn't cut your trip in half, but it's like a measurable and noticeable number of minutes. I want to say it's like 30 minutes or something. And if you're coming from China and you're doing a direct flight, I mean, you know, it's probably even more because that's such a farther distance and you're going across the whole ocean and everything. So those things make a difference. Okay. All right. So we're going to keep inertial reference frames. We're going to keep relative motion really simple. I want to start by, that's not it, looking at a video. I can't remember if there is sound on this, but I think I made the sound come through. Okay. So relative motion is determined by the person observing it. So we have a person here who's sitting on a subway station, a subway platform, and here comes the train. Okay. So to the person on the platform, like we are, the guy in the orange jacket isn't moving, right? But and the people on the train are moving. However, if I flip it and now I'm a person in the train, it looks like the platform, the station, and the person standing on it is moving. But the person sitting next to me on the train, they're not moving. And I don't feel like I'm moving because everything around me is moving with me. And that may have been all there was. Okay, so let's kind of break this down and talk about this, all right? So here's going to be my train platform. Here is going to be you on the ground. Okay. And I see a train go past. And my train is going to move this way. The train. And there's going to be a person sitting on the train. my green person. And for the person sitting on the train, like I just said, it feels like the train isn't moving, but that you standing on the platform are moving. Okay. But now we're going to make things more complicated, because now there's going to be a person on the train who's walking, who's moving. Okay. And that's going to be my person P. Now, my person sitting on the train, my green person, sees the person walking on the train moving with a velocity pt, person with respect to the train. Okay, and that would be if you were sitting in the train and the person's walking and you see that they take, you know, that they've moved 10 seats in 10 seconds, and so maybe they're walking like a meter a second. Figure the seats are a meter apart. Okay, but you're measuring that with respect to the seats, which are in the train, which are moving with you. Okay. So maybe we should write here that VP is the V of the person with respect to the train. Can I do that WRT? Do we all know what that means? With respect to. Okay. Now, with respect to, what can't you read, Dagny? What can't you read?
Oh, no,
Oh, okay. Oh, okay. It looked like you were like
yeah.
squinting. Okay. So if I'm on the ground and I want to look at the velocity of the person with respect to the ground, okay? It's you actually. You are standing on that train platform and you want to know what the real velocity, not the real, but you want to know what the velocity of that person is with respect to the ground. How are you going to find that? What's it going to be? Tia. Yeah, it's going to be the train's velocity, the person's velocity with respect to the train, plus that velocity of the train. And you should have a feel for that intuitively. That if I'm walking on the train, just like I'm walking on the airplane or I'm jogging on the cruise ship, I'm doing whatever my own little local motion is, but that object itself is moving. Okay. And if you think about it in terms of an airplane, you know that. You got on the airplane in Buffalo, you got off the airplane in Los Angeles. No matter how much you walked around on the airplane, you also traveled that 3,000 miles. Okay. So eventually we will get to the point where we fill it in, so we can fill it in right now. It usually when I teach this, it clutters it up and people are confused at the beginning, so it's easier just to call it the velocity of the train. But we will eventually do that. Okay. All right. So this is kind of the intuitive approach. Based on things that you know from your life, this equation should make sense. But as we may or may not have said before, things that make sense out there in the hallway do not necessarily translate into making sense in the physics room. Okay? Because there are all kinds of things that you know out there that don't count in here. Such as when I slide something off the table and it lands on the floor, what's its velocity? What's its final velocity? Well, if you were out in the hallway, you'd think it was 0, right? Because it stopped moving when it landed. But in here, we know that that's not how we think about it, okay? So just because something makes sense in the real world with your real world experiences doesn't mean we can just pick it up and translate it into a formula in the physics lab, okay? Some things work, but not everything. So let's kind of do this a little more formally and see if we can come back to that equation, okay? So just like we kind of drew this diagram with respect to velocities, we can draw our systems and start with displacements, okay, or distances. And we're only going to be moving in one direction, so distance and displacement will be the same thing, okay? And in fact, x position and distance and displacement are kind of going to all end up being the same thing. So I have a coordinate system here, and that is going to be coordinate system u, which I should say slash ground. Okay, because you are standing on the ground at the station observing all of this. Okay, and your origin is going to be back here, and you are going to be standing at the origin. I don't really need a vertical axis at this point, but it's nice to just have a line where the origin is. Okay. And then I've got another coordinate system that's the train. It's not necessarily vertically displaced, but it's easier to see that if I kind of draw them a little separated. Okay, we're still worried about or learning about relative motion in one dimension at this point. Okay. And then I have my walking person, who I am still going to call P. Okay. So now here is where we go crazy with respect to subscripts. Okay. So you on the ground can measure the distance between you and the back of the train. You can also measure the distance between you and the person, which is going to be the position of the person with respect to you or with respect to the ground. Okay. And then we can also label the position of the person with respect to the back of the train. So there's another coordinate system that starts at the back of the train. Okay, everybody understand what I'm labeling? So based on our extensive knowledge of vectors and geometry and life, we can say that the position of the person with respect to you is equal to the position of the person with respect to the train plus the position of you with respect to the train. Yeah. In general, yes. Here's a little, here it's a little wacky, and we're going to fix them in a minute. Okay. Annabelle.
So when you have like the position of percentage, right? So when you're like figuring out what to add just in any like given situation, there would always be like one like there's trains the whole time.
Yes. Yes, and we will talk about, as your book did a little bit, we'll talk about a way to kind of put those together and how to put them together and how to make like the chain. But right now, I'm honestly basing this just on looking at the picture. Okay. All right, so this was a snapshot in time. Okay, we could call it, if we wanted to, t equals 0. Okay, and then we could talk about a time t later. And again, you aren't moving. You are still standing back here. But the train has moved. Because trains move, it's what they do. Okay, and the person has moved. They are walking on the train. Okay. So again, I can label this distance here between the train and the person. And I'm going to call it XYT prime. Not prime like derivative prime, okay? Just like as opposed to my original value, okay? And then this from the back of the train to the person is going to be X person with respect to the train prime. And then there's going to be X person with respect to you. And again, there's going to be a little prime symbol there just to show that it's changed. Good. It probably goes after the X. It really kind of goes on top of the subscript, but I would do X prime and then the subscripts if you were typing it out. Okay. And again, just by looking at the situation, I can say that X prime PY is going to be X prime YT plus X prime PT, right? Which is very similar to that first equation that I have up there. Okay. So let's pretend for a moment that everybody's moving at a constant speed. Okay, not the same speed. We're always going to assume that the train moves at a constant speed. Okay, but let's just hope for a minute that the person is walking at a constant speed. Okay, so I'm going to take these two equations and I'm going to subtract this one from this one. Okay, so that's going to give me X prime PY minus XPY. And then XPT prime minus XPT plus XYT prime minus XYT. Nope, I just took two equations and I subtracted one from the other. And then placed the parentheses as the omniscient narrator that I am. Which is why I get to be a teacher, because I am an omniscient narrator at this point in time. Okay. And then How long did it take this motion? How long did it take this change in position to occur? T. So I could really, whoops, divide both sides by T. And before you ask me why I wrote that the way I wrote it, think about it. Algebraically, if you're going to tell me, well, I can't put T under both things because then I have 2 squared, you don't. Stop and think about your math. Okay. So, what's a change in position over time? Velocity. Okay, so this is going to give me the velocity of the person with respect to you or the ground. This is going to give me the velocity of the person with respect to the train. And this is going to give me the velocity of the train. Okay, which is what I had earlier. We have flex. I have to say that uniform circular motion and relative motion, like there's not a lot of activities that you can do with it. So I know there's going to be a lot of talking, but when we start forces next week, it is my intention to, next week, it is my intention to bring some more activity in so that it's not just me standing here talking at you. Okay. All right, so this is the equation we had at the beginning, right? If we go back a couple slides, right there. Okay, I interspersed ground and you, but it's the same idea. Okay, so if you want to, we could say the velocity of the person with respect to the ground is equal to the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. And when we do the example, we'll talk about this even more, but the idea is that we're trying to set up a chain. So I kind of think about it as a chant. So I've got the velocity of the person with respect to the train. I ended on the train. So the next thing I have to have is the velocity of the train with respect to something, in this case, the ground. Okay. And as your book, I think, tried to tell you, these like inner indices should be the same when you're adding things up. It's one of those ways that can help you figure out if you're right or wrong. Okay. And then the indices that are left over should be the indices that are what you're looking for. Okay. So I wouldn't use that as a hard and fast rule. It's more of a logical guiding principle kind of thing. Okay. All right, so this takes care of velocity. This shows us how velocity works for relative motion. Okay. Are we good? Everybody got what they need? Okay. So if we've talked about position and we've talked about velocity, what's the next thing we have to talk about? Acceleration. Okay. Now here's the point where we decide that we are freshmen in college and we are going to make this easier. We are not juniors or seniors taking relativity. Okay. So as far as we are concerned with relative motion, the reference frames are moving at constant velocities with respect to each other. Okay. So that means effectively that VT or VT ground is equal to a constant. at constant velocities with respect to. Okay. But the person on the train can accelerate. That person can walk faster or slower and change their rate, change their speed, their velocity. Okay. So if we go, okay, but person on the train can change their speed, okay? In which case they have an acceleration, and we want to know what that acceleration looks like on the train and what that acceleration looks like to somebody who's standing on the ground or at the train station, to you. Okay. So I'm just going to go back to the equation I had, which says the velocity of the person with respect to you is equal to the velocity of the person with respect to the train plus the velocity of the train with respect to the, actually, I'm not going to say ground, I'm going to say you. Okay. Now, we are getting very close in calculus to being able to do derivatives, okay? Hopefully we're going to start like power rule and chain rule and all that jazz today, if not tomorrow, okay? So we are pretty much ready to come back to this part of physics where we can start taking derivatives, okay? So what is always the definition of acceleration? What is acceleration always equal to? Tia. Right. And if we decide to use big person rules, adult rules, freshman physics rules, okay, that means that the acceleration is always equal to the derivative of the velocity. What's up? Oh, yep, I can. There we go. Okay. So that's always true. Just like velocity will always be the derivative of position with respect to time. Okay. And in fact, we will next week, do problems like this in calc. Okay. So we will take some time and kind of backtrack in physics and do some of those examples once we have the calculus that we need to do them. Okay. So what I'm going to do is I'm going to take the derivative of both sides of this with respect to time. Okay. And that d by dt or d over dt just is an operator that says take the derivative. Just like when you see that radical symbol, that's an operator that tells you to take the square root. Okay. And we will come across in calculus many more ways to indicate to take a derivative. Okay. So I'm going to take the derivative of the whole thing term by term, which I can do because it is a operator that distributes, like addition or multiplication. Okay. So remember, the derivative of velocity is by definition acceleration. So this is going to be the acceleration of the person with respect to you. And then this is going to be the acceleration of the person with respect to the train. And then my last symbol here is the acceleration of the train with respect to you. But what do I know about that? It's what? No, it is in fact technically constant, but it's a very specific constant. It's 0 because does the velocity of the train with respect to you change? No. Okay, that is an assumption, a condition that we put on the physics that we are able to do because we can't do all the physics yet. All right, we are nowhere near ready to do electrostatics or quantum mechanics. Okay, so this is equal to 0 because my assumption is, my condition is that I do not allow my reference frames to accelerate with respect to each other. They are at constant speeds. Okay. So this tells me that the acceleration of the person with respect to you is the same as the acceleration measured by somebody sitting on the train. So the acceleration that's measured is the same in both reference frames. Okay. Makes sense? All right. So let's try that first example problem about the boat traveling upstream. Okay, so I think that's example 1. All right, if somebody would read that for us, please. Let's just stop there. Okay, and then we'll deal with the kid in a minute. Okay, so new type of problem, but it's still a problem. What's the first thing we do when we solve a problem? We draw a picture. Okay, so here's my river. It's not really a good brown. Okay, here's my boat. Okay. And I know some things, right? What kind of things do I get from the problem? Dagny, what's one thing? With respect to the water. So the boat water is 14 kilometers per hour. And we'll even write upstream because we're going to talk about what that means. Okay. Annabelle. No, if these are problems where, I mean, you're not going to, when you do a problem like this, you're not going to be using chapter 2. Okay, it's just not going to, most of the times things build, but this just makes it way too complicated. Okay, and I've never, I won't say never, I have rarely ever seen a problem like this on the AP, but I did go to the College Board because I thought, oh, maybe I'll skip this. And it is listed as something you need to know how to do. So that's why I'm keeping it. Okay. What other piece of information do you have? Lauren. So that's going to be the velocity of the water with respect to the ground is what? 9 kilometers per hour. Okay. So let's go back to that upstream thing. Does anybody know what upstream means? Dagny. That doesn't really answer my question the way I need it answered. Tia, and then I'll let the boat people figure tell me. Yes, it is against the current of the water. So that could kind of be what upwind is, but upstream isn't the same thing as downwind. Downstream would be the same thing as downwind. You're going in the direction of the flow but upstream means you're going against water. Okay. So again, omniscient narrator that I am, I'm going to let the velocity of the water with respect to the ground go that way, go towards the left. And I'm going to let the velocity of the boat with respect to the water go to the right. And then what's missing from my picture? Tia. I kind of figure the ground's there. Fiona? No, I'm going to assume that person's on the ground. Nope, I had that. That's the velocity. No, that doesn't belong on my picture. That's what I'm going to find, but that doesn't belong on my picture. There's something really basic missing from my picture. I'm not necessarily, because I don't really care about, I'm not calculating how far it moves, but you're on the right track. X0 is the same kind of idea for the thing that's missing here. Nope, I wouldn't put time on a picture. Nope, that's what they're talking about. I don't really need to know where the origin is. What? Nope, I know what my reference frames are. I've got the water and the ground. What does V stand for? What's velocity? What kind of a quantity is velocity? A vector. What does a vector have? Direction. What's missing from my picture? Direction. Which way is positive and which way is negative? So I'm going to assume that positive X is in that direction. Okay. Right, because this is in one dimension. Yeah. This is just like the original problems that we did where we had things rolling back and forth. Okay. So for my part A here, what am I trying to find? Okay, the velocity of the boat with respect to the ground. And it is important here to give it subscripts, to give it a label that makes sense in the context of the problem. Okay, and we'll talk about this in calculus in another several weeks, maybe not till Thanksgiving. Okay, although Thanksgiving is really only like a month away, right? 5 weeks. Cool. Okay, but I want to label it boat with respect to the ground because the rest of my letters have B's and G's in them. Okay, the rest of my symbols. So now you want to build that formula. So the velocity of the boat with respect to the ground, I need to start with any velocity that I have for the boat. So I know the velocity of the boat with respect to the water. But that's not what I need. So I need to add something to that. I need to add the velocity of the water with respect to something. And what do I have? With respect to the ground. So I'm going to add to that the velocity of the water with respect to the ground. Okay. So notice that all of these have little vector symbols over them. Now I'm only in one dimension, so I'm just worried about whether it's positive or negative, but I still have to take that direction into account. So what's the velocity of the boat with respect to the water going to be? What? Positive. So it's going to be positive 14 kilometers per hour. And this is a situation where we can leave it all in kilometers per hour. Everything has the same unit. It's not worth changing things. Okay. And then what's the velocity of the water with respect to the ground? Kilometers per hour, right? So what are we going to get? Positive 5 kilometers per hour. So if you were standing on the shore, okay, on the ground, and there was a seagull that was just floating in the water, not moving its feet, okay, that seagull would move in the direction of the water. The boat is also moving in the direction, is affected by the motion of the water, but it also has its own motion. So you would be sitting on the shore and you'd see the seagull go this way, but you'd see the boat go that way. Okay. All right, let's see if we can, in less than a minute, do part B. So part B says now we have a kid on there, right? And my kid starts at the front of the boat and walks to the rear with a velocity, we'll call him child, with respect to what? The boat. And what do I want to find? The velocity of the child with respect to what? The ground. Okay. So now I'm just going to add something else to my chain. I know the velocity of the child with respect to the boat. I know the velocity of the boat with respect to the water. And then I know the velocity of the water with respect to the ground. Okay. And my kind of inside indices, my indices that are next to each other are the same. And I kind of think of that as they collapse each other. But the thing I'm left with is child and ground. Okay, so my velocity of the child with respect to the ground is going to be equal to, what is the velocity of the child with respect to the boat? Is it positive or negative? I'm sorry. Yeah, the child with respect to the boat. Is it positive or negative? Negative. And how fast is that kid walking? I know that the velocity of the boat with respect to the water is positive 14 kilometers per hour. And then the velocity of the water with respect to the ground is negative 9 kilometers per hour, right? So we do not need calculators. What does that give us? Negative 1 kilometers per hour. So if you're sitting there on the shore and you can see things on the other side, so like you're sitting outside Mississippi Muds enjoying your ice cream and you can see Grand Island on the other side not moving, okay? The boat's going in front of you, but even though the boat is moving this way, if you're looking at stuff directly across, the child is moving backwards. It's freaky, but true. Okay, so do you understand how we're putting these things together? Okay, then I will let you clean your desks because the bell will ring. Do not do the relative motion homework. I mean, you can try it if you want, but it will probably be due Tuesday because we don't have class tomorrow. It's drop day. Monday, we will finish up 2 dimensions, but Monday we will also start forces. I'm in the process of making the reading guides. Don't take them yet. I will email you when they are ready for you to kind of pull. Okay, Lauren? Sure. Which homework? Sure. Hang on, let me see. Guess, are you okay? Okay, then I'll see you later.